Hello, my name is Harrison Newman, and I was assigned problem B. So for this problem, we imagine a boat of height h, length L, width W, and immersed in liquid up to height h prime. As boats do, it travels at velocity v parallel to its length L such that the cross-section is minimized, and for this, in this problem, we are instructed to approximate the cross-section of the boat with just a simple rectangle of height h and width W. And in this case, it is a square. For all intents and purposes, we are going to be working with boats that are immersed in liquid water and surrounded by air where it is not submerged. And so the first goal we're going to have to do is find h prime so that we know which portion of the boat is above the water and which portion is below the water, because these two portions are going to have different coefficients of drag. Now we have the ratio we need, which is the density of the object over the density of the fluid. And since we know that that is multiplied by the original volume of the object, we know that this proportionality is going to be applied also to the height, because we are going to take the density as constant over the total volume, which is not totally accurate, but is a decent approximation for our purposes. So h prime equals h times density of the object over density of the. For a Panamax ship, dimensions are typically 290 meters by 32 meters by 32 meters, and they typically have a mass of 52,000 tons when they're loaded up, or 52 million kilograms. So the volume of the ship we find by just multiplying the dimensions together. We get 296,690 meters cubed. And to find density of the boat, or rowboat, we use 52 million kilograms over 296,690 meters cubed, which is just the mass over the volume. And we get 175.1 kilograms per meters cubed. So we take rowboat, put it over row of the fluid, which for water is 1,000, and we get 0.1751, which then we multiply by h to get h prime. So we find that the depth that the boat is in the water is 5.6 meters. So to find the drag force Fd, we use the equation Fd equals 1/2 density of the fluid, velocity squared, CD dot A, where A is the cross-sectional area, in this case 32 by 32, and CD is the drag coefficient, which is going to be 0.2 under the water and 0.8 above water. Now, these ships typically move around 9 meters per second, and we already know the density of the fluid is going to be either the density of the air around the ship or the density of the water. So under the water, we multiply this out, use density of the water, which is 1,000, and we get 1.452 times 10 to the 6 newtons. Now, if we do it in the air, we multiply all of this out, except we use 1.225 kilograms per meters cubed for the density, and this makes a pretty big difference because this only comes out to 3.353 times 10 to the 4th newtons. So in this case, the water is clearly dominating. It's a couple factors higher. But now that we've found the force, let's think about it a little bit. Is the drag force dependent on mass? So we can say that the drag force is dependent on mass because we know that Fd equals 1/2 density v squared CdA, where A is equal to the height times the width. Now we know here that the height is dependent on the mass, as the height of the water h bar leads us to A equals h prime dot density of the object over density of the fluid, and density of the object is equal to the mass of the object over the volume of the object. So while it's not very directly obviously dependent on mass, we still had to use mass to find h prime, which is a very important part of this, to finding out the drag on this object. So we now can move on to say, what is the energy used from any point A to B because of drag? So we use the work equation, which work equals the integral from A to B on f dx, and we can pretty much just set whatever A is to 0, because this depends on the distance and the total distance, not just the displacement. So if the distance, let's say from Sydney to LA, is 12,000 kilometers, then we just set A to 0, set B to 12,000, do the integral, which is just 12,000 times the force, and we get 17.826 gigajoules. And that is all we're doing today. So thank you for watching.